In order to get ready to implement EKF on an enhanced self-correcting cell model, we need to find the partial derivative matrices A hat, B hat, C hat, and D hat. Once we have all of those set, the rest of the EKF implementation is fairly straightforward. We'll do that in the next section, and we'll also talk about how we break up the code a little differently in that section. But for now, our focus is on finding these derivative matrices. And we start by looking for the components of the derivative components of the state equation to find A hat and B hat. We have defined and reviewed the enhanced self-correcting cell model, but inside that model we considered only the deterministic inputs. We didn't talk about the stochastic inputs. So how do we do that? Sorry, I moved something by mistake. We're going to say that W, the process noise, models something unknown in the current sensor measurement. So the true cell current then is going to, instead of being IK, it's really going to be IK plus WK, but we measure the IK part of it only. When we do this for the state equation, we do something a little different in the measurement equation, we'll see. And there's probably a number of different design approaches to what would make sense with how we define the noises and where they get input into the model equations. This is simply one example of it, and you might be able to find other ones that work just as well or better. We are going to assume that the coulombic efficiency of the cells is exactly 1. And we know that's not true, but we also know that the EKF has a kind of a feedback built in, and we're going to rely on that feedback, the adaptivity, to handle whatever small error is introduced by assuming perfect coulombic efficiency. And I think we've already seen that eta k is usually between about 0.99 less than eta k is less than 1, so we're not too far off with our assumption. We are then going to write the state of charge equation of the model as zk plus 1 equals zk minus delta t over q times I plus wk. And what you see there is that the eta, which was there, is 1, so that is no longer visible, and we are parenthesizing current plus w in this integral of coulombs being counted. We need to compute the derivative of z with respect to previous z, and that's just simply 1, and the derivative of z with respect to w, and we see that's minus delta t over q. In this equation, Q is measured in ampere seconds. If we do happen to measure in ampere hours, which is maybe more common, there would be a factor of 3600 Q instead of just plain Q in the denominator. So that's a choice of how we write the equation. You have to do unit analysis always to make sure that what you're doing makes sense. Those are the components of A and B hat, A hat and B hat, that are needed for the state of charge equation. We start looking at the diffusion equation. We say first let's talk about time constant tau j being e to the minus delta t over rj cj, which is the time constant of that particular diffusion mode. Then if I define that short form, then the resistor current state equation can be written for any number of resistor currents in parallel RC branches as new resistor currents equals this diagonal matrix with all the time constants tau on the diagonal times old resistor currents, and then plus 1 minus the time constants times the input, and we notice again the input is I plus W. I'm going to call this first matrix A sub RC and the second matrix B sub RC. And when we do that, and we take, in this case, the vector derivative of I at the next time step with respect to I at the present time step, we get the matrix result A sub RC. So this is using vector calculus as opposed to just standard calculus. And then when we do the same thing with respect to the W input, we get B sub RC. Time to move on to the hysteresis state. If we define a hysteresis factor AH to be e to the minus, notice again, current has W added to it, gamma delta T over Q, where Q is again ampere seconds. If it's ampere hours, that has to be 3600 Q in the denominator. Then I can write the hysteresis state equation as new hysteresis equals AH times old hysteresis plus AH minus 1 times sine of this noisy input. Taking the partial derivative of the state equation with respect to the previous H, we just get AH bar, which is AH evaluated at the previous at this W bar input. And in order to find the B matrix, what I need to do is I need to take the partial derivative of this expression with respect to W. Now this is actually somewhat tricky. This AH is a function of W, so I need to take that into consideration, and so is that AH. I need to take derivatives of both of those. But the sine function here is non-differentiable. The sine function looks like that, and at 0, the derivative is a delta function. And that's a big problem. You know, above 0, the derivative is 0. Below 0, the derivative is 0. Everywhere else is okay, but right at 0, we have a big problem. So you ask a mathematician and they might say, well, you can't use an EKF on this system because the equations are not differentiable. However, we're going to do some engineering kind of approximations and say maybe they're differentiable enough to get some reasonable result out of EKF for a battery model. What we're going to do is make a couple of assumptions. We'll assume first, what if I plus W happens to be bigger than 0? If we happen to know that, then I can take the derivative of the sine function because it's away from the non-differentiable point. And I did this in Mathematica, so I believe it's right, but you can go through and double check if you'd like. You could take the derivative of this expression and remembering that W is inside of those components also, and find that the partial of H with respect to W is the equation that I have listed here for I plus W bigger than 0. Then we play the other mind experiment where we say, well, what happens if I plus WK happen to be less than 0? And we take the derivative then, and we get that equation right there. And they're very similar, but there is a difference between the two of them. So what we're going to do overall is we're going to combine these equations, and our combination, now notice, if you will, that this here is what we called A bar. If I substitute W bar in this derivative, I would get A bar H comma K, and same with that. So I'm going to combine these two equations and say what is similar. Minus, 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 this term, that term, the AH bar, AH bar, AH bar, and then on the right here I'm multiplying all that by 1, and then I need an expression that takes into consideration what's happening with HK, and I say, oh, if I plus W is positive, I have a positive. If I plus w is negative, I have a negative. Let's just suppose, I know it's not differentiable at 0, but suppose if I plus w is 0, that 0 is an okay thing to do. I replace that plus minus sign with simply the sign of I plus w bar, multiplying by h hat. So this is a design decision because mathematically I can't implement a derivative, but this here is an approximate derivative. Maybe I'll say it's approximate. It's true when the sign of I plus w bar is not 0, but when the sign of I plus w bar is 0, we're approximating by this. Couple more equations to consider. One of them is the zero-state hysteresis or instantaneous hysteresis in the model. And this hysteresis state says if the current that I measure is not negligible, then I assign Sk to be the sign of what I measure. Otherwise, I keep the previous version. Well, getting a negligible current can happen, but here, let's suppose it's a 0 probability event. And in such a case, I just simply say, let the partial be 0 with respect to both of those. That's a choice as well. If it wasn't 0, then not a 0 probability event, then I would have to do this differently. All of that discussion so far in this section has looked at A hat and B hat matrices by examining the state equations. Now we look at the output equation, the voltage equation, to determine C hat and D hat. I've reminded you here what the model output equation is. It says voltage equals open circuit voltage function evaluated at the present state of charge plus the magnitude of the zero-state hysteresis times the value of zero-state hysteresis plus the magnitude of the analog hysteresis, if you will, times that hysteresis state minus the diffusion and minus I sub I times R and then plus a sensor noise. In this expression, we no longer consider I to have W noise added onto it, and that might be cheating a little bit. We could have said I plus W here, but that actually adds an enormous level of complication to the problem because the filter generally assumes, the equations we've used have assumed that the sensor noise and process noise, in other words, the noise added to the state equation and the noise added to the output equation are uncorrelated with each other, but here I would be adding R0 times W to the output equation and adding V to the output equation, so there would be definitely a correlation between W and the noise on Y. So it can be handled. It's quite a pain to handle, and it's beyond our scope to handle it, but the Kalman filtering course 5550 talks about how to do that. Here we're not going to. Here we're going to say, well, let's say everything is dominated by, all the noise is dominated by this right there. Now I have to take derivatives of the output with respect to different components. So the state components and the sensor noise component. Derivative of output with respect to the SK state, well, it's linear in that state. It's just M0. With respect to hysteresis state, just M. With respect to the diffusion currents, just the resistor associated with those currents. With respect to the sensor noise, just 1. The last thing that we need to be able to do is compute the derivative of the output with respect to state of charge, which is computing the derivative of the OCB function with respect to its input state of charge and evaluate it at the present state of charge estimate, prediction, Z hat K minus. We can approximate that relationship using OCB data or a curve fit to the OCB data. Here we're going to say, suppose we have a table of state of charge zk and OCV of zk is my table with a bunch of numbers in each column. How can I use that table to find the derivative of OCV with respect to zk? And this little piece of code is one way to do that. And it's a MATLAB function that you can implement. So function docvz equals docv from SOC, evaluated at SOC, that's the present operating point, the OCV relationship. This is the table. So SOC is this, OCV is this, and then this is the operating point where I want the derivative to be found. I'm assuming that the table entries are evenly spaced in SOC, so the difference here, dz, is the difference between any two of them, so it's SOC2 minus SOC1 in my table. And I'm going to use a forward and a backward difference method and average them together, which is basically a central difference, in order to find the derivative approximation. So first I use MATLAB to find diff of OCV with respect to z, which divided by dz, which is basically a derivative itself, except the length of the output is one fewer than the length of the input, and that causes us a problem. So I'm going to take the derivative and shift it over one and pad on the left, and I'm also going to add one entry padding on the right, and add those two derivatives together, divide by 2, which is basically a central difference derivative approximation. Then from this central difference approximation, I take the derivative at my desired point by interpolating from the original SOC curve, but now I've added a DOCV column, and I interpolate at the desired point in order to get the DOCV by DZ at that point. Now, interp1 in MATLAB is horribly inefficient. You could do this manually using a bunch of extra code, and it turns out to be a lot faster, but this is the idea, and this will work. In this figure, I show the derivative of open circuit voltage with respect to state of charge plotted versus state of charge for 6 different cells. And you might remember we plotted open circuit voltage for 6 different cells in 5710 at one point, and these are the same cells, and these are their derivatives. Just to give you an idea what the output looks like. So there it is. There's a little bit of noise and ripple and so forth that probably is not a real physical thing. It's probably just some numerics plus measurement error. So it's possible that you could filter these results, smooth them out a little bit, and get somewhat better, a better derivative, but it's not really necessary to do so because the derivative is simply a scale factor in the EKF code, and if I scale, suppose this result here should be 1, but instead it's 1.001, that little bit of noise makes very little difference in the operation of the filter. So the ripple's okay. If I did filter, I'd have to be very careful because filtering adds lag. It shifts things over. So I would have to use something called a zero phase filter in order to do the filtering properly, which amounts to filtering forward and filtering backward, and then combining the two results in such a way that there was no group delay, no phase shift in your derivative. So it's complicated to do it right, and it's not necessary to do it, in my opinion, so I would advise you not to unless you've got a really good reason to do so. So this was the hard part in implementing an extended Kalman filter on an enhanced self-correcting cell model, that is coming up with the derivative matrices A hat, B hat, C hat, D hat. Here we've come up with all the components of the matrices, and when we look at the code, we'll put all the components together. But once we've done this part, everything else is fairly routine. We are going to restructure the code a little bit in our next example for a more realistic operating scenario, and you'll see how we do that. But the core of the code you'll also see is basically the same as what we've seen already.